Good morning, everybody. Let's get started. Good morning. Let's get started with the class today. So we're going to talk about Base Theorem and do some examples, couple of examples, and then continue with probability and related stuff. We're going to start also talking about counting, fundamental counting rule, and then factorial and some other things, okay? Permutations, combinations, and then probably also some other formulas that we need to talk about. So anyway, let's get going. I kind of want to go back and remind you of something, like some of the things that I have done, and then we are going to review it very briefly, and then we are going to go ahead and do the Base theorem. Probability. So that's where we are at right now. So probability is the chance of some event happening, and we define the probability of an event A. We define the probability of some event A as the number of times the event A has happened divided by the total number of times we have tried. So that's the relative frequency definition of probability. And then there are some properties of probability. I just briefly mention some of them. So for an event A, the probability of event A must fall between 0 and 1, right? Then also probability of the event A plus the probability of its complement must always add up to 1, right? So probability that event A will happen plus the probability that A will not happen. A complement means what is not in A, meaning that it didn't happen. So if A is the event that something has happened, A complement is the event that it did not happen. So the probability of event A plus the probability of A complement is always equal to 1. And then also probability of the sample space. So I could label them if I want to, maybe 1, 2, 3. Probability of the sample space is always 1, right? Then number 4, if an event A is a collection of simple events, that means A is equal to A1 union A2 union ... union AN, then the probability of A is the same as the probability of individual events. So probability of A1 plus probability of A2 plus ... plus probability of AN. And this is only when AI I is 1, 2, 3, all the way up to N. AIs are simple events. Okay. And the fifth property is this. If A is the empty set, okay, probability of the empty set or probability of phi is always defined to be 0. So these are some basic properties of probability that you want to keep in mind. Okay. So these properties, basic properties of probability, you want to keep in mind. Make sure that you know these things, and when you are using probability, you kind of use these properties. Okay. So when I ask you for the probability of some event A, don't give me a number like negative 0.5. Okay. That would tell me that you have missed the basics. Or use the property that probability of an event A plus the probability of its complement is always 1. Probability of the sample space is once. Remember, sample space, we define it as the collection of simple events, right? Sample space is the collection of simple events. And what is a simple event? Let's call it SI. An event, SE I meant, not SI. An event that can happen in only one way or a unique way. Happen in only one way. What is a simple event? An event that can happen in only one way or a unique way. There are not multiple ways of that event happening. Next, the properties of probability. So addition property of probability of A union B is probability of A plus the probability of B minus the probability of A intersection B. The easy way to remember this thing is using the Venn diagram. If this areas, if this circles represents the probability of A, left one, let's say, represents this probability of A, this represents probability of B areas of this circle, then this middle area, you're counting it twice. Once you're counting with probability of B, another time you're counting it with probability of A. Since you're counting it twice, you're subtracting it once because you're supposed to count once. So this is Venn diagram. This is easier way to remember. So one property of probability, and number two, probability of A and B. We have defined it as probability of A times the probability of B, given that A has already happened, or probability of B times the probability of A, given that B has already happened. Now, another thing we talked about is mutual exclusiveness or disjoint. Mutual exclusiveness slash disjoint means that probability of A intersection B is 0. Mutual exclusive, we also use the definition, two events A and B are mutually exclusive if the intersection of these two events is the empty set, right? And then if you take probability of this equation, both sides, the probability of A intersection B is equal to probability of the empty set, right? But remember, the probability of the empty set is what? Right here, empty set is 0. So probability of A intersection B is equal to 0. So next, the other property that we talked about, independence, right? Let's write down independence. Independence. Two events A and B are independent if probability of A, okay, is the same as the probability of A given that B has happened. Meaning, just because B has happened, that's not going to have any impact, or it's not going to change the chances or likelihood of A happening, or equivalently. So make sure that, what happened to my Apple Pencil? It's saying battery is low. I charged it for a while. Equivalently, probability of B given that, probability of B is the same as the probability of B given that A has happened. So that's what it is. So this is what it is. Basically, I just summarized everything that we talked about probability, okay? It's in a nutshell, all the things that we talked about so far about probability, and have given you sufficient examples to explain these concepts. So please do make sure that you are okay with these concepts because we are going to need them. Okay, Base theorem is conditional probability. Oh, actually, I need to add one more thing, which is the conditional probability. The conditional probability is probability of A given that some other event B has happened. Okay, so probability of A given that something else has happened. So sometimes we need to find conditional probability, and Base theorem is a great example, a great theorem that could be used to solve real world problems. Using Base theorem, we can find out a lot of, or we can solve a lot of interesting problems. And I'm going to go ahead and give you a couple of examples. Okay, so you may want to even take a picture of this page if you'd like. This would help. Okay, this is kind of like a collection of everything that we talked about for probabilities. Any question, guys, before I move on? Anybody? Any questions? No questions? Everybody okay? All right. Okay. I took this little time to charge up my pencil. Hopefully it'll charge. Okay. Now let's go ahead and clean up this space here. Bring back the thing. And let's see. We talked about these things. So here is a typo that I kind of want to address in the homework. Okay. So this is what it is. Two events are independent. So there is a question in the homework that asks you, what is the definition for two events being independent? Two events are independent. I just talked about it. Probability of A is the same as the probability of A given that some other event B has happened, or probability of B is the same as the probability of B given that some other event A has happened. Now, there is a problem here in the homework where you cannot put this parenthesis. Look here, I'm missing that for some reason. In that particular problem, you cannot close this parenthesis. So what I want you to do, this is a technical glitch. So what I want you to do, put probability of A is equal to probability of A given B, and try to put the parenthesis and try to kind of play around with it. You will get it right. But even if you get it wrong, no worries. I will not penalize you in the ultimate grade because it's a bit hard to do this. Maybe I should change the problem to just multiple choice as opposed to giving you a text box answer for it. Okay. So let's go ahead and keep that in mind. If you're having difficulties with this, try to type it in this way one by one and play around with it. So what I recommend is that you go ahead, type P, uppercase P, open parenthesis, A, uppercase A, close parenthesis, then put equal to, then uppercase P, open parenthesis, A, vertical line given, B has happened, and close parenthesis. And try to type it in as it is. And you will see that this parenthesis starts bringing another additional parenthesis here. So just type it in and hopefully it will work. It's just one particular problem that we are having difficulties entering the answer. Okay, has anybody tried this, ran into issues? I know at least a couple of people have emailed me about it, and I emailed them personally. And I told them that I was going to address it in the class.
Excuse me?
Yes.
I actually tried it, but when I put the P and then A parentheses, like at the beginning, it would mark it wrong. So I put P parentheses B, and then the rest was like PA/B, and it marked right. So I don't know if like others have the same problem, but for me it worked with the B first.
Okay, so try instead of A, try B. Okay, probability of B is equal to probability of B given that A has happened. So yeah, thank you for sharing your thoughts. Any other questions, anybody? All right, let's move on to our Base theorem. Okay, so I'm going to remind you of Base theorem. I'm not going to derive it again. So probability of A given B is equal to probability of B given A. Flip it, okay? Multiply it by the event that's given, multiplied by the probability of the event that's been given. So probability of A, all of it divided by the probability of the event that's given in the left side. So probability of B. And this is exactly what I have here. And you can switch the A's and B's. Now we have used this formula briefly last time. I think I did this traveling salesman problem last time. I finished it. All right. So do you guys feel that you're okay with the traveling salesman problem? Or would you want me to go over this again? Because this is a bit of a difficult topic. Are you okay with it? Everybody okay? All right. So let's move on, okay? If you get stuck, please watch the last video, okay? That way you will get it. So let me warm you up with a little bit of interesting probability problems. Think of this scenario. You have three balls. Ball A, which has 10 red, let's say. Ball B, which has 10 white. And ball C, which has 5 red and 5 white balls. Okay. If you randomly select a ball, what is the probability that it is a red ball? So this is a completely random situation. So you have three different balls. First one has, or one of them has 10 red, one of them has 10 white, and the other one has 5 red and 5 white balls. Okay. You randomly select what is the probability that you randomly select a ball that is red ball? Okay. What is the probability that you randomly select a ball that is going to be red ball? So let's say R is the event that the ball you select is red. Okay. Select a red ball. A is the event that you selected from bucket A or ball A. Okay. B is the event that you select ball B, and C is the event that you select ball C. Now you randomly select a ball. You randomly select a ball, and what is the probability of having a red ball? So in essence, what it is asking, find the probability of selecting a red ball. Now, if you select a red ball, how could it happen? What could happen? How could you do that? So think of it this way. If you select a red ball, you could be selecting it from ball A or ball B or ball C, one of these three balls, right? So technically is going to be the probability of selecting red ball and it's coming from ball A. You could select a red ball, it is coming from ball B. Or you could be selecting a red ball, it would be coming from ball C. It couldn't come from anywhere else because these are the only three options. So you could select a red ball from bowl or bucket A. You could select a red ball from bowl or bucket B. You could select a red ball from bowl or bucket C. And what is the probability of these individual events happening? Remember, they are mutually exclusive. What it means that you couldn't be selecting one red ball from multiple buckets. So that means it cannot happen that you are selecting a red ball, but it's coming from both A and C, or A and B, or B and C. So these events are kind of mutually exclusive. So the probability of selecting a red ball would be the sum of all of them. You add all of them. Okay. Probability of selecting a red ball is you sum all of them. So I'm going to do one of them. So let's take the background off so that you have a bit more space. So first find a probability of red and coming from A. Okay. So which, by the way, could be defined as probability of event A times the probability of red given A. So pay kind of closer attention here. This is one way of defining it. What if we do this? Probability of red times the probability of selecting A, given that you selected red. If you try to use this version of the formula, both are equivalent. This one and this one are equivalent. If you're trying to use the second one or the bottom one, you'll run into problem. Why? You're trying to find this probability of R. So this is what you're trying to find. So you really can't do the problem. You'll get stuck. So if you get stuck in this problem somehow, somewhere, what you want to do is try the other version of the problem. Okay, other version of the definition. That would help you. So let me go ahead and do the problem for you. Now, let's see what's happening here. So we are not going to use this one. This one. We are going to use the top one. What is the probability that you will select bucket or bowl A? There are three of them. If you do it randomly, it's going to be 1/3 times. What is the probability of selecting a red ball if you select bucket A? So that means you selected this one. What is the probability that you will select a red ball? The fact is that here you have 10 red balls. If you selected red ball, bucket A or bowl A, your chances of selecting red is 100% or 10 out of 10. Because there are 10 balls, so if you select bucket A, you will be selecting a red ball for sure. So you multiply it by 100% or 10 over 10. I do 10 over 10, right? So this probability, so let me use a slightly different color. This probability is going to be 1/3 times 10 over 10. Plus, we are going to find the next one, which is probability of red and selecting B, which again, if you go this way, you'll run into problems. So you're going to do probability of selecting bucket B times the probability of selecting a red, given that bucket B has been selected. So what is the probability of selecting bucket B, which is 1/3, right? If these buckets are selected randomly, there are 3 of them. So your chances of selecting one of them is going to be 1/3 times. What is the probability that you will select a red ball if you select bucket B? That answer, by the way, is going to be 0 out of 10. Why is it 0 out of 10? Because middle bucket, or the bucket B, has 10 white balls. It does not have any red balls. So it's going to be 0's chance that you will select a red ball if you select bucket B. So it's going to be 1/3 times 0/10, plus the third probability, again, similarly, is going to be probability of red and C, which is going to be probability of selecting C times the probability of selecting a red ball, given that you have selected C. Now, having said that, probability of selecting C is 1 out of 3, right? There are 3 buckets. So it's going to be 1/3 times the probability of selecting a red ball. If you select C, is going to be interesting. There are 5 reds and 5 whites. So there is a 50% chance of selecting a red ball, or 5 out of 10. So it's going to be 5, sorry, not that. It's going to be 1/3 times 5 out of 10. If you add these numbers, it's going to be, first number is 1/3, because 10 and 10 cancel out. Second number is going to be 0. And the third number is going to be 2, 1/2. So 1/3 times 1/2 is 1/6, right? If you add these numbers, it's going to be 2/6 plus 1/6, which is 3/6, which is 1/2. How did I go from here to there? So I just multiplied this by 2 and this by 2, so that I had the common denominator. 2 times 1 is 2, 2 times 3 is 6. So that's what it is. So there is a 50% chance that you'll select a red ball if you randomly pick a bucket and pick a ball. Is this okay, everybody? Everyone okay with it? Any questions, anybody? No questions?
No, you're good.
Good, all right. So let's go ahead and clean up the screen. Now, I kind of want to do an interesting problem. This is something silly, but yet it's kind of funny. So this problem, I'll do the first two, because the third one, I forgot how to solve it. Maybe if time permits, I'll look it up and solve it to you. Third one is a bit funny. They have different answers, by the way, kind of. So the first one is, if a couple has 2 children, but the older one is a boy, then what is the probability that they will have 2 boys? So you have a couple who has 2 children, but the older child is a boy, or maybe the younger child is boy. I don't think it really matters. So then what is the probability that they will have 2 boys? What do you think? What do you guys think? Tell me.
I solved one of those in the homework. Isn't it you do boy boy and then you do boy girl, girl boy, girl girl, but you crossed out the girl girl because it doesn't count since it's telling you the older one is a boy.
Mm-hmm. Sure. You're right. Then what is the answer?
Would it be 1/3?
Okay. Good try. I like your approach. Anybody else wants to kind of pitch in here? Anybody else has any thoughts, suggestions? One last chance for everybody. Anyone has Any suggestions? No? Okay. Who was it that commented? Can you please tell me your name?
Maribel?
Maribel? Okay, great. That's right. So let me do the problem in a simple way, using common sense. They have two boys, okay? What's given? First one is a given fact is that the first one is a boy, right? Then what is the probability that the second one is going to be a boy? So let's say A is the event that the first child is a boy. Okay, B is the event that second child is a boy. What in essence we are looking for is probability of having a B, event B, or the fact that the second child is a boy, okay? Given that the first child is a boy, that's what you're looking for. If I formulate this problem in probabilistic equations or notation, what you are looking for, probability of B, given that A has happened. What it means is that the older child is a boy, or older kid is a boy. That's what you're looking for. So what is the probability of event B given that event A has already happened? That's what the question is asking. Now I'm going to get to this, but before I get to this explanation, I'm going to think of it like an ordinary person. Okay, you guys should think of it that way. Don't make it more complicated than it has to be. If you already know that the first child is a boy, what are the chances that the second one is going to be a boy? As an ordinary person who does not have a lot of knowledge about probability and all those complications, what do you think?
You have a 50-50 chance of having a boy or a girl.
Yeah, thank you, Alicia. You have a 50% chance. Because just because you had the first child boy, is it going to say, hey, second time you have to have a boy? Or is it going to influence, hey, you have the first time boy, the second time it has to be a girl? Does it have any influence on the second child? The answer is
No.
no. Just because the couple had the first baby, a boy, it will have no influence or no bearing on the second child, because it's not going to say just because you had the first one boy, you have to have a certain gender in the other one. There is no bearing or there is no influence. That means they are independent. So the second one has as much of a chance of being a boy or being a girl, which is what? 50%. Okay, so the answer to this question is 50% or 0.5. Okay, 0.5 or 1/2, whatever you put, which translates to this: probability of B given that A has happened is the same as the probability of B. That means it doesn't matter what happened, but probability of giving birth to a boy, okay, the second child being boy, is just 1/2 or 50%. That's how you should be thinking about the first problem. Okay, probability of giving birth to a boy second time is nothing but 50%. Is this clear to everybody? Please do keep in mind that these probability problems could be confusing, and it may seem that you may make mistakes, and it's likely that you may make mistakes, and I do make mistakes too. Okay, these probability problems are a bit tricky. So sometimes it takes a lot longer to think about it, okay? And then conditional probability and Bayes theorem is not easy. So it takes a little bit of thinking and a little bit of struggling with the problems and the concepts before you get a somewhat better feeling about them. All right. So if you make mistakes, please don't feel that, oh, you can't do it, or I'm not good at math. Trust me, I have been teaching this for many years, many years, and still I make mistakes. So don't beat yourself if you don't get it right. Okay. Don't be too harsh on yourself or hard on yourself. Just keep thinking, keep an open mind. Don't think with emotion. Think objectively what it should be. Then you'll probably get rid of some of the issues. We kind of tend to think based on our experience, or sometimes we tend to think, oh, okay, yeah, this is what it should be. Kind of like gut feeling. So avoid those things. Now, the next one is an interesting. This one I don't do because I forgot the solution. How to do it. This is a bit slightly complicated, but it's kind of fun. So the next problem is, by the way, I got these problems off the internet. So if a couple has 2 children, and I forgot who the author was anyway, I think I saw it in a couple of places, so maybe it's open problem. If a couple has 2 children, this time look at the wording. I'm going to highlight it. It says, but one is a boy as opposed to the older one is a boy. But one is a boy as opposed to the older one being boy. Then what is the probability that you have 2 boys? And what is it that you think, you guys?
Wouldn't that one be 1/3?
Who is talking?
Maribel.
Maribel, why 1/3? Yes, the answer is probably 1/3. Let's figure it out. Anybody else? What is it? Just getting the answer in and of itself is not 100%. That's good, but you have to be able to explain your answer. That's the important part. Why is it 1/3? I think it is 1/3.
I did it like how you did like the first one you showed us about the 3 children.
Oh yeah.
I did it that way. So I did
boy. Uh-huh.
But I only did 2 boys since it's only 2 children.
Exactly.
So I did the possible ways of the 2 children.
Okay, exactly. Great. Thank you. And I think there was another person, I forgot who it was, who kind of thought along the same line. So first of all, you're having 2 children. How could it happen? You could have boy, girl, boy, and girl. This problem is kind of tricky. So a couple has 2 children, but one is a boy. One is a boy. Okay, what is the probability that they have 2 boys? So the interesting thing is this cannot happen. Why can it not happen? Because it says that one of them is a boy. Okay, one of them is a boy. So implicitly here, one of the things that kind of makes the problem a bit interesting is that one of them is a boy. It implicitly kind of calls for ordering things. Boy, girl is not the same as girl, boy. So that probably is an implicit assumption here. So anyway, when you say one of them is a boy, this option is out of question. You cannot have girl and girl. So one of them is a boy, so you are left with three different options, okay? Three different ways of this event happening. Now, out of these three things, we are only interested in this one, boy, boy. The chances of that happening is 1 out of 3. 1 out of 3. That's what it is. And by the way, these problems are, again, it could be a bit confusing, and sometimes it could lead to a little bit of misunderstanding. So just try to think about it a little bit. Now, how this problem is going to change if we think that the order doesn't matter, then we are running into an interesting scenario where we could be thinking of 1/2 or something like that, probably. But the order does matter. One of them is boy. That means we are saying the first one versus the second one. So that's why the answer is this, probably. So, and now a couple has 2 children. One is a boy and he was born on a Friday. Then what is the probability that they have 2 boys? And the author gave some interesting explanations, and explanation for this is kind of interesting, how things change, or how you should come up with the probability given that the boy was born on a Friday. It really doesn't matter whether it's Friday or Sunday or Monday. Just born on a particular day, how it changes the probability. But this one is a bit involved, and I forgot the answer to this, so please ignore that one. If time permits, I'll look at it and tell you. Next interesting problem. So that's the one we kind of want to talk about. Oh, before I do this problem, I want to do this. This is an interesting problem, and some of the smartest people have made mistakes. Some really top-notch mathematicians, they made mistakes on this problem for a while. And there was a newspaper article on this. I think at the end, some lady from Indiana or from somewhere, she solved the problem. There apparently used to be a show, and you can Google it. There was a show. It's called Monty Hall Show. So it's kind of funny. So in the show, you would have 3 doors. Door 1, let's call it door 1, door 2, or door 3. 3 doors. Behind these 3 doors, there will be one door that has a car. And 2 other doors is going to have goats. Okay? I'm just going to go ahead and talk about it. Give me 1 second, okay? Now, let's go ahead and look at this problem. So the way this game is played is this. As a player, at the beginning, you pick one door, okay? One of the 3, it doesn't matter. Let's say you pick door 1, okay? As a player, you pick one door, and then the host of the game, what he's gonna do, Monty Hall, he's gonna pick one of the other 2 doors. But when he picks that door, let's say he picks door number 3, okay? So as an player P, you pick door 1, and Monty Hall picks door number 3, it has a goat for sure. If you pick door 1, Monty Hall is gonna pick one of the other 2 doors that for sure has a goat. Now, to increase your chances, should you stay with the door that you selected, or should you jump to the other door that Monty didn't select? Given that there is only one car behind these 3 doors, and there are 2 goats. Again, 3 doors, You randomly select one door. Let's say you selected the first door. It doesn't matter which door you select, okay? You could select the second or the third one. Then the Monty is gonna pick one of the other two remaining doors that has a goat for sure. Okay, if you were to select the middle door, then Monty is gonna select either D1 or door 1 or D3 or door 3. And whatever he selects, for sure, that one has a goat. Now, to increase your chances, should you stay with door 1 or should you jump to the remaining door that is not selected by Monty Hall? What do you think? This is kind of an interesting problem. I think many people made mistakes on this problem, including some smart people, very smart people, mathematicians. And it's kind of interesting. So what do you guys think? I kind of want to get your feedback on it. Should you stay with the door 1 or should you move to door 2 to increase your chances of winning the car? What do you guys think? I want people to join in. Think of it as a game show.
Does Monty know where the car is when he selects the goat?
Yeah, he has to know. He would know, but he wouldn't tell it to you.
Then no.
Otherwise, he couldn't pick the door with a goat, right? What if he picked a door with a car? Then the game is not going to work. He knows which one has that car. So he's for sure going to pick a goat. What do you guys think?
Monty is going into the game show with a biased opinion because he already knows the answer.
But Monty is not the player though. So it doesn't matter. So he's not winning the car. People from the audience are playing the game and they are going to be the ones who are going to be winning and they don't know. As a matter of fact, Monty is kind of helping them in a way. He's saying, oh, okay, you picked this door. Now I'm going to pick one of the other two doors that has the goal. So now you have more of a chance to win the car. Monty will never select a door that has the car behind it.
So then you might switch doors.
Well,
Knowing that.
I'm sorry, you might switch door. Why? So the question boils down to, should you switch the door to increase your chances or should you stay? If you stay, then you're saying that, oh, there is a 50-50 chance. There are two doors, right? 50-50 chance. So it doesn't really matter whether I switch or not. Only time you'll switch if you think that you have a higher chance of winning the car by switching. So
maybe Monty didn't select door 2 because that one is the car.
What is it?
Maybe he didn't select door 2 because that's where the car is.
Okay, who is talking?
Brandy.
Brandy, okay, good. Anybody else? Anybody else wants to pick? Any other explanations from anybody? Nobody? Nobody wants to talk? Okay. Thank you, Brandy, for your explanation. I kind of like it. Actually, you explained the problem in a way that kind of makes sense, but you did it like a person who is kind of like not thinking mathematically, doing it kind of like an ordinary person, how an ordinary person would do it. And yes, your answer is right. You just hit on the head of the nail with a hammer here. So let's say Brandy picked this door, okay? Door 1. And then Monty goes out and picks door 3 because Monty knows where the car is. So she's saying that, okay, since Monty knows where the car is, and he's not gonna select that door, maybe this door has the car, so she's gonna switch. So that's a good way of thinking. As a matter of fact, that's a great way of thinking. Maybe the car is on the other, behind the other door. Otherwise, he would have selected it. But then there is also an argument. Maybe, Brandy, you already have selected the car. In that case, it really doesn't matter. Maybe you don't know which one is it. Maybe you already selected the car, okay? Maybe you already selected the car, you don't even know. In that case, both of these have got. So this one has got and this one has got. So it really doesn't matter which one Monty selects. He could select door 3 or select door 2. In either case, it's gonna be what? A goat. So then there is this argument too, Brandy. But without spending too much time on the problem, you can do the problem like this. So car, goat, goat. That means first door has car, second door has a goat, third door has goat. Or goat, car, goat, goat, car, or goat, car, goat. These are the only 3 ways this could happen. So let's say you selected the first door that has a goat, okay? Let's say, then Monty is either gonna select this one or that one, okay? So so let's see, the first one has a goat, okay? That means you're restricting yourself to these 2. This cannot happen. The top one cannot happen if you have goat in the behind the first one. So if you select this, then Monty is gonna either select this or this. That means either the third door or the second door. Now the problem boils down to this. Initially, when you select, you have 1/3 chance, okay? Initially, when you select any door, doesn't matter, your chances of winning is 1/3, okay? Because there is one car out of 3 doors, okay? Behind 3 doors, there is one car and the other 2 are goats. So you have a 1/3 chance. Now, let's say Monty exposes that this one is goat. Then should you stay in door behind, with door 1, or should you move to door 2? What in essence tells you is this: there was a 1/3 chance associated, 1/3 chance associated with door 3 of being a car, but that chance is right now 0 because Monty has already opened the door and showed it to you that it is a goat. Then where does this 1/3 go? Many people argued that this 1/3 is going to be divided equally between door 1 and door 2. So that means half of 1/3 you add to this, and half of 1/3 gets added to this. So it's going to be 1/3 original chance plus half of 1/3. That means this probability is going to be getting distributed equally between door 1 and door 2, which gives you 50% chance, okay? 50% chance. If you have 50% chance, then you really shouldn't change. If you really have 50% chance in each of these doors, door 1 and door 2, given that we know door 3 is a goat, then you should not change your position at all because you have equal chance of winning. However, counter to your intuition, it turns out that this 1/3, that probability, remember, total probability has to be 100% or 1, right? Total probability has to be 100% or 1. Initially, we had 33.3% here, right? 33.3% here and 33.3% here. You selected door 1, so you have a 33.3% chance of winning the car. But Monty selected, let's say, the third door. Now, the probability of having a car on the third door goes down to 0 because we know that it is a goat. So if you know something for sure, the probability becomes either 0% or 100%. Okay. Now, this 33%, is it going to be divided equally between door 1 and door 2? In that case, you should not switch at all. Then 33% plus half of 33.3% is going to be 50%, and similarly 50%. So this will come down to 50% and 50%. You should not change in that case. It really doesn't matter. However, the interesting thing is that this 1/3 or 33.3% does not distribute equally. It actually, all of it goes to the second one, the one that has not been opened. So you have 67% chance of winning the car if you switch from door 1 to door 2. But if you stay with door 1, you have 33% chance of winning the car. So you will be better off switching your door, meaning if you switch your door about 67% of the times, you're going to win the car, and 33% of the times you're going to lose the car. So if you want to increase your odds of winning, you switch the door. And Brandy, I kind of like it, the way she explained it. She said, oh yeah, maybe he knows that the second door has a goat, so I'm going to switch. I mean, second door has a car, so I'm going to switch. Yes, intuitively, if you think of it that way, you get to the right conclusion. And they, by the way, have done apparently simulation, computer simulation with this kind of scenario, and it does happen. So these are the 3 ways that could happen, and doesn't matter which door you pick, right? That door has 1/3 chance, but then between the other 2, then Mr. Monty is gonna pick that with a goat behind it. Then the probability of having a car behind that door is 0. Then that probability switch to the other remaining door. Okay, that's what it is. All right, let's move on. I thought that was kind of a fun topic. I didn't actually, honestly, I didn't give you the full explanation of it. Maybe I'll do it later by going over these examples. I need to get to the breast cancer problem. So where is my breast cancer problem? There it is. So this problem is going to take a little bit of time. So everybody, let's get to this. Let's take a quick 5-minute break. I'll quickly come back and let me drink a little bit of water, okay? I'll quickly come back and we'll reconvene. And you guys have had a lot of probability. So this problem is a bit more difficult and it requires your thinking. So I want you to be fresh, okay? So let's take a quick 5 minutes break. So right now about 9:34, 9:35-ish. So let's meet at 9:40 exactly, okay? Don't even get out of Zoom, stay here, all right? Okay, guys, so it's been 5 minutes, it's 9:40 exactly. So let's get started. So we're gonna talk about breast cancer problem. So this problem is a little bit tricky to understand the wording and everything. So we are gonna spend good amount of time working on this problem. First, let me read the problem. A mammogram is 90% accurate. So it is 90% accurate in correctly predicting breast cancer in a woman, which means it's true positive. That means someone has cancer, breast cancer, and that individual takes the test and comes out positive. So that's the true positive. And 15% inaccurate in predicting it. That means false positive. So these 2 terms kind of throws people off because we are not a medical science people, we are ordinary people. These academic terms kind of throws us off. Think of it this way, in layman's terms. You know, in the general population, some women have breast cancer. So if the woman actually does have a breast cancer, she is tested. If she's positive, that's good. I mean, not good. I meant to say that's correct. Obviously, that's never a good thing. I meant to say that's correct outcome. However, if she does, so which is true positive, okay? Now, on the other hand, if she has breast cancer and does the testing, but the answer is negative, that's not good. Why? Because the person is thinking that she does not have breast cancer, but in reality, she does. That's false negative, okay? False negative. So on the other hand, the person does not have breast cancer, okay? If the test result is negative, then it's good, okay? That's the situation we hope for everybody, right? Or we'd like to get to someday for everybody. So the person does not have breast cancer and she's tested and the test result is negative, that's good. However, the person does not have breast cancer, but the test comes out positive, that's an alarming news. That's false positive. Okay? That's false positive. So these are the terms that you need to get used to. The best way to do this problem, from my experience I have seen, is this, creating a little table, and that's exactly what I'm gonna do. And put these numbers in context. In the general population, 1% of the women between the ages of 40 and 50 have breast cancer. If a woman tests positive, then what is the probability that she has breast cancer? Again, in layman's term or in ordinary people's term, you don't care about the math, really. What do you care about? A woman went for testing, okay, she tested positive. She would like to know, does she have breast cancer or it's a false positive thing? She would like to know, does she have breast cancer? Now, it's not true only about breast cancer. Anything. Somebody goes to the hospital and tests for HIV. The test comes out positive. Does the person have HIV or not? Somebody tests for heart disease, and doctor says you have heart problem. Okay, after doing some testing, and then you would like to know, do you really have heart problem or you do not? So now think of this little table that I'm gonna create right now. Let me just do it here. Let's define a event. C is the event, someone has breast cancer. Okay, and C prime is the event that the person does not have breast cancer. Okay, plus is the event that tests positive, and minus is the event that tests negative. Okay, so let's define the events clearly. So a person, a woman, either has cancer or she does not have cancer, C complement or C prime. What are the chances of having cancer in the general population? 1% chance, or 0.01. If your chances of, or if a woman's chance of having breast cancer is 1%, what are the chances that she does not have breast cancer? That would be 99%. 100% minus 1% is 99%. Then the other scenarios, complementary, plus for testing positive, minus for testing negative. Plus for testing positive and minus for testing negative. Now, let's take this wording. This verbiage is kind of like throws people off, and it did throw me off too. So don't Don't feel bad. 90% accurate in correctly predicting breast cancer. Okay, 90% accurate in correctly predicting breast cancer. What it means is this: the person has breast cancer and tests positive. So that means has breast cancer and gonna test positive. Okay, that's gonna be 90%. That's true positive. On the other hand, person has breast cancer, but it doesn't test positive. That means it's negative, it's false negative. It's gonna be complement of 90%. You can either test positive or negative. There is nothing in between for the sake of argument. There is no inconclusive answers. So if you have a test, if you have a cancer, then you test positive, which is correct diagnosis. On the other hand, if you test negative, that's a wrong diagnosis. If the person has cancer, but the test came out to be negative, that's a wrong diagnosis. So this is a scenario. I'm gonna use a red color here. This is a scenario we want to avoid. And there is another scenario that we want to avoid too. I'm gonna show it to you shortly. Now, if you read the second statement, 15% inaccurate, not accurate. Here it was accurate. Here, 15% inaccurate in predicting it. Okay, so what it is, that means the false positive part. So other scenario is that the person does not have cancer. That means you're going to be in the second column. You either have cancer or you do not have cancer. If you do not have cancer, then the test results are bad 15% of the times. Okay, so that means it's inaccurate test. So you do not have cancer, but somehow they say that, oh, you do have cancer. That means test positive. That's a bad scenario. You don't have it, but they do tell you that you have it. On the other hand, if you do not have breast cancer and the test results come out to be negative, look here, negative right here in this row, then it's okay. It's good, right? So 100% minus 15% is 85% or 0.85. So this is good, 0.85%. This is good or correct outcome. You don't have the cancer and you test negative. And then the top left corner, okay, you have cancer and you test positive. So this one and this one are correct diagnosis, whereas this one in red and the bottom red one are incorrect diagnosis. And incorrect diagnoses are the bad ones, particularly if you don't have cancer and somebody says you do, not good. Okay, that's bad. On the other hand, it's also bad that you do have cancer and the doctors can't find it. They say, oh, you don't have cancer. So both of these scenarios, both of these red boxes, red circled items are not good. Those are incorrect diagnoses. Now, is the table clear or I made it complicated for you? Is everybody following it? Or some of you following it?
Yeah.
Okay. Think of it in a simple term. You either have cancer or you don't. They tell you that there's a 1% chance that you have cancer. Okay? There is a 1% chance that you have cancer. Then 99% chance that you do not have cancer. Then you can test positive or test negative. Now you can test positive when you have cancer, which is correct diagnosis, but you can also test positive when you do not have cancer. That's a bad diagnosis, which is this one. On the other hand, you can test negative when you have the cancer, which is wrong diagnosis here. On the other hand, you can also test negative when you do not have cancer. That's a correct diagnosis. Now, I'm gonna create the table again here, just so that you can see it clearly on this. Someone has cancer, 1% chance. Does not have cancer, 99% chance. You test positive or you test negative. And this is 0.9, and this is 0.1, this is 0.15, and this is 0.85. The diagonal from bottom left to top right, that's the incorrect diagnosis that you want to avoid, this red one and red one. And diagonal from top left to bottom right, that's the correct diagnosis, all right? Now, the person wants to know this, probability of C, that means probability of having cancer, given that the person tested positive. Now that's the probabilistic formulation or mathematical formulation of the problem. As an ordinary person, you go to the doctor, they test you and they say, you have cancer. You want to know, do you really have it? That's what the question is asking. This question is asking, if somebody goes to the doctor and the doctor tests for breast cancer, and the person asks the question, do I really have it? Did the doctor make a mistake, or did the test go wrong, or was there any other issue? So you want to know, okay? So we take that real world problem and formulate it into conditional probability. This is nothing but a conditional probability. Probability that a woman has cancer, given that she has already tested positive. That's what we would like to know. Now, look at the Base theorem. So let me use a different color so that you can see it slightly clearly. Oops, what happened? Did I pick a different color? Okay. This is equal to probability of positive given C times the probability of C, all of it divided by the probability of testing positive. That's exactly like the formula I have had. Probability of A given B is the same as the probability of B given A times the probability of A, all of it divided by the probability of B. You can replace A by C and B by testing positive, okay? You can replace A by C and B by positive or testing positive, okay? Then you will see that it comes down to this. I just took this Base theorem and put it here. Now, let me just take the background off. Now, we need to find a couple of things. What is the probability that someone has cancer? Which is pretty easy, is given. Probability of C is 1% or 0.01. Okay, times. What is the probability of testing positive given that someone has cancer? So you have to kind of think about it. Given that someone has cancer, so that means you are in this column or in this column. What is given? That you have cancer. That's given. Now you couldn't be in this column or you couldn't be in this column. If you know that you have cancer, or if it is known that the individual has cancer, then the person could not be in the right column, has to be on the left column. So if that is given, so if you are restricting yourself to the first column, which comes from the fact that C is given, that means the individual has cancer, then what are the chances of testing positive, which is nothing but 90% or 0.9. So you're going to multiply it by 0.9. Now, the next thing we need to know is the bottom part, testing positive. What is the probability of testing positive? So this is something interesting. This is where many students go wrong. What is the probability of testing positive? the probability of testing positive. How can you test positive? Two ways that could happen. You can test positive and you have cancer. That means you do have it. Or also you could test positive and you do not have cancer. And these are the only two ways that could happen. Since C and C primes are mutually exclusive or disjoint, so you can just add the probabilities. Okay? C and C prime are complements of each other. They're mutually exclusive or disjoint, right? So probability of testing positive and having cancer plus the probability of testing positive and not having cancer. If you add them up, that's when you get the probability of testing positive. Now we are going to have to do this thing. So again, make sure that you pick the correct formulations. The probability of cancer times the probability of testing positive given the person has cancer. On the other hand, if you go this route, probability of positive times the probability of cancer given positive, then you will run into problem because this is what you're looking for. So don't use this one. Similarly, probability of C prime times the probability of testing positive given C prime. Okay. Now, if I take these two and come up with the numbers, what is it going to be? Probability of having cancer is 0.01 times the probability of testing positive given that someone has cancer, which is the first column, that's 0.9. So 0.9 plus probability of not having cancer or C prime is 0.99. That means this one, probability of not having cancer is 0.99 times. Now, probability of testing positive given that someone does not have cancer, this time does not have cancer, that means you're restricting yourself to the second column. So what are the chances that you will not test positive when you don't have cancer, which is 15%. So it's going to be 0.15. And if you multiply these two numbers, what do you get? Let me see. 0.9 times 0.01 plus 0.99 times 0.15. That's 0.1575. So probability of testing positive is 0.1575, which is the bottom number. So this is 0.1575. Now, if I do the math, that's going to give me the probability of having cancer given that the person has tested positive, which is this, right? Is going to be equal to, so 0.9 times 0.01 divided by 0.1575. It comes out to be approximately 0.0571 or approximately 5.71% chance. So if someone tested positive, the probability that the person actually has breast cancer is pretty low. It's 5.71%, at least mathematically. I should say mathematically it is pretty low. The person has 5.71% chance. The reality is probably different. I'll get to that later. Now, this is how you do this problem. Are you guys okay with it? This is how you do the first part of the problem. Any question? Is it too complicated? Are you guys okay with it? Everybody? Ken, William? Is it okay, Ken?
Yeah, I understand.
Maribel, is it okay?
Yes.
Anybody, if you are not clear, let me know. I'd be more than happy to go over it again. Okay, all right, let's clear it up. This is a problem students struggle with. So what I'm gonna do, now I'm gonna unclutter it and make it even a bit clearer by having this problem again. By doing this again, I'm gonna actually repeat the problem, what I did, so that you guys are absolutely sure. Probability of having cancer is 1%, probability of not having cancer is 99%. Testing positive, testing negative. So if you have cancer and you test positive, that's 90% of the times. You have cancer, but you do not test positive, that's 10% of the times, or 0.1. Then you do not have cancer, but you test positive, that's 15% of the times. You do not have cancer and you test negative, that's 85% of the times. This is given in the problem, but in a very compact format and hard to decode sometimes for ordinary people. What we are looking for is the probability that someone has cancer, given that the person tests positive. Remember, C is the event that an individual has cancer, and positive sign is the event that tests positive. Okay, so you'd like to know what is the probability that someone has cancer, given that the person tests positive. So this is going to be probability of cancer given tested positive is the same as the probability of positive given cancer times the probability of the cancer, all of it divided by the probability of testing positive. All right. Now, this is the same as probability of cancer, probability of testing positive given cancer, which is the first column, probability of testing positive given that you have cancer. What is given is C. That means that restricts you to the first column. Then if you're restricted to the first column, what are the chances that you will test positive, which is obviously 0.9. Okay, so this is going to be 0.9 times what is the probability that someone has cancer is given in the problem, 1% or 0.01. Similarly, testing positive. So when can you test positive, or how can you test positive? You can test positive in two ways. You can test positive when you have cancer, that means testing positive and have cancer. And you can test positive when you do not have cancer. These are the only two ways you can test positive. So the first one, testing positive and having cancer. So it's going to be probability of cancer times the probability of positive testing, given that you have cancer. Second one is going to be probability of cancer. Oh, sorry, this is C prime. I made a mistake. Sorry, C prime. So probability of C prime times the probability of positive given C prime. So first one, probability of cancer is 0.01 times probability of testing positive given you have cancer, which is just, we just did it here, 0.9. You're restricting yourself to the first column, so 0.9, plus probability of C prime. That means you do not have cancer, which is 0.99, times the probability of testing positive when you do not have cancer, or C prime, right? Which restricts you to second column, which is going to give you 0.15, 0.15. If you add these two numbers after multiplying them, okay, you get 0.1574. 5. So your bottom number, probability of testing positive, becomes 0.1575. If you do the math, that gives you probability of having cancer, given that the person tested positive, is approximately, this is approximately 5.71%. Now that's what it is. So if someone tests positive, then what are the chances that the person will have breast cancer? That's about 5.71%. If this were to be a reality, I think people would stop going to the doctors. 5% or 6% of the times doctors are correct, 94% of the times, doctors test results and the conclusion by the doctors are correct, and 96% of the times is wrong. That's not good. What in reality happens, this is an abstract or theoretical calculation. Okay, in reality, when you go to the doctor is not going to randomly select a person and say, hey, we are going to take you and start testing you for breast cancer. But the way this problem is designed, it actually does that. This is for a randomly selected person from the population. This, be careful in understanding. If you randomly select a woman from the population and test the woman for breast cancer, there is this is correct, about 5.71 or 6% chance that the person would actually have cancer if the person tests positive. Okay, this is randomly selecting a woman, okay, from the population and testing the person. Okay, it's kind of like you as a person. Okay, you randomly select a woman from the population and say, hey, go ahead and please test yourself for breast cancer. And it turns out that she tested positive. Now, what are the chances that she actually has it? About 5.71% or about 6%. However, when you go to the doctor is not going to do that. Doctor is going to actually talk to you, look at your family history, look at your medical records, this or that, and look at your symptoms, most importantly. Medical doctor is an expert. They spend years and years, and in some cases, lifetime, or in many cases, rather, they spend lifetime specializing in something. So when they see one, they know one. Okay, it's kind of like me talking to a student who is trying to take statistics class. I can talk to the student for 15 minutes and figure out what level he or she is, whether he or she is likely to pass the class or no. Where does it come from? It comes from experience. So when a doctor sends you to test for a breast cancer, doctor is not just taking a person off the street. Doctor is analyzing individual patient or individual people who are going to him or her with these symptoms and these conditions. Then doctor might guess, oh yeah, in that case, this probability, if the doctor says, yeah, you may have, these are the symptoms I'm seeing, that kind of resembles what a person with breast cancer would have, then obviously, yes, the chances of actually having cancer, given that the test result is positive, is much higher, because a doctor is very comfortable in identifying the lumps in the breast of a woman. So if the doctor sees there is a lump, then he would know, or from the size of the lump, he would probably or she would probably know whether it's likely to be cancerous or no. So this is just an abstract or theoretical problem. Now, I spent a lot of time on this problem on purpose. I want to make sure that you understand this is not an easy problem. This is probably the hardest problem in the entire class. Now, let's go ahead and do the second part of the problem. I'm not going to erase it, so please read it with me, okay? Here it is. Find the probability that someone has breast cancer given that the person has tested positive second time, not first time, second time. So the person already tested positive, but to be sure, they go back and test again. Okay, then what is the probability that the person actually has cancer? Now I'm going to create the table again, and only difference is going to be this. Again, you test positive, you test negative. You have cancer or you do not have cancer, C prime. These numbers do not change. Testing positive and testing negative, they still stay the same. What changes is this. When you test negative, when you test positive for the second time. So remember, we are trying to find out this probability of having cancer, given that the person tests positive twice, not once, but twice. So you are not going to test second time unless you test positive first time. You know that. That's an assumption we are making. You are not going to test second time unless you test positive the first time. So this time, if you are testing second time and getting positive, your sample is coming from people who already tested positive once. Somebody who already tested positive first time is the sample, is the population, not sample. Sorry, I meant to say population. Somebody who tested positive once, that's the population you're considering. On the other hand, in this problem, or in the first part, you didn't consider that. You considered your population being the general population. In the second problem, the key difference is that your population changes. This time, your population does not have 1%. This time, your population does not have 1% cancerous people, or people with cancer rather, not cancerous people, wrong wording. People with cancer. So this number is going to change to 0.05. Let's say roughly, technically it should be 0.0571, but I'm kind of rounding it. So there is about 5% chance that somebody has cancer, given that the person has tested positive. Now, if you have 5% chance of having cancer, then 95% chance of not having the cancer. Now go back and here, look here. Okay, let me use red. Here, it was 1% versus 99% because it came from the general population. Here, it doesn't come from the general population. It comes from a special population. That population has 5% cancer because they already have tested positive. If they have tested positive, the chances of having cancer is about 5% right here. Now, the rest of the problem is easy. You just do this and this. So I'm going to bypass it here. I'm going to write it. No, maybe not. Let me just write it here. Probability of cancer, given that the person tests positive twice, is the same as probability of testing positive twice given cancer times the probability of cancer, all of it divided by the probability of testing positive twice. So now probability of cancer second time is 5% or 0.05 times probability of testing positive twice, given that the person has cancer, is approximately 90% or 0.9. Now this bottom one, you have to do it exactly the way we did it, except that this number is gonna be 0.05 times 0.9, that doesn't change. And this number is gonna change to 0.95 as opposed to 99 times 0.15. 0.15, okay? So let me do the calculation. Maybe, give me a second. I want to erase it and then write it properly so that you can see it. Plus 0.99 times 0.15. Sorry, not good. I meant 0.95 times 0.15. Now, if I do the math, what do I get? 0.05 times 0.9 plus 0.95 0.95 times 0.15. That gives me 0.1875. So there's gonna be 0.1875. That's the probability of testing positive twice. Okay. So this is gonna be 0.1875. So let's do that math. 0.9 times 0.05 divided by 0.1875, which is 0.24. 0.24 or about 24%. Let me just double check to make sure that I got the numbers correct. Okay. 0.05 times 0.9 plus 0.95 times 0.15. Yeah, so about 24% chance. So probability of having cancer, given that the person has tested positive twice, is about 24% or 0.24. Now, here I ask you, find the probability that someone has breast cancer, given that the person tested positive a third time. So this time we are looking for probability of cancer, given that the person tested positive 3 times. Oops, not even 2, 3 times. Now, how are things gonna change? Now this number is gonna change to, can somebody tell me what this number is gonna change to? Can anybody tell me what this number is gonna change to? Third time. Anybody, please? Alicia, what is this number gonna change to? I can't hear you.
Would it be 0.24?
It would be 0.24. Thank you, Brandy. This would be 0.24. So I ran out of space. I'm gonna clear it, okay? So let's even take the background away. So this is gonna be, so C 0.24, C prime is gonna be 0.74, right? 76. Because 100 minus 24 is 76, or 100% minus 24% is 76%. Testing positive, testing negative, this is 9.9, this is 0.1, this is 0.15, and this is 0.85. So now the probability of testing positive, having cancer, given that the person tests positive 3 times, is gonna be probability of testing positive 3 times. So this is not really positive. Technically, this is testing positive 3 times, right? Or third time. So testing positive for the third time, given that the person has cancer, times the probability of cancer divided by probability of testing positive 3 times, right? And if you do the math, probability of cancer now is 24% or 0.24. Probability of this is going to be 0.9. Testing positive third time, given that the person has cancer, is 0.9. Now, probability of testing positive for the third time is going to be probability of testing positive for the third time and C, plus the probability of testing positive for the third time and doesn't have cancer, which is going to be probability of cancer, which is 0.24. I'm not going to write it again, times the probability of testing positive given the person has cancer, which is 0.9, plus 0.76 times 0.15. So these numbers give me 0.24 times 0.9 plus 0.76 times 0.15, 0.33. check my numbers. I'm doing it on the fly. So probability of testing positive 3 times is 0.24 times 0.9 plus 0.76 times 0.15, yeah, 0.33. So this is going to be 0.33. So if I simplify this, I'm going to get probability of cancer, given that the person tested positive 3rd time, is going to be 0.9 times 0.24 divided by 0.33, which is approximately 0.6545, which is equal to 65.45%. So 3rd time, if you come out to be testing positive, it is going to be, you have about 65% chance of having the cancer. And remember, this is an ideal scenario where you randomly select a person initially to start off with the in the population. Okay, you don't select it in a very specific way. It's just a random person being selected from the population. So if you can do it right, what are the chances of having a cancer if you test 4 times positive? So probability of having cancer, given that you test positive 4 times, you could easily do it. Now this number is going to change to what? That number is going to change to 0.65, let's say, and then this number is going to change to what? 0.35, and everything else is the same. So that's how you do it. Is it okay, guys? Everybody okay? Any question, anybody? I think I spent a lot of time on this problem, so I kind of wanted to make sure that you understood it. If you understood it, the rest of the problems from Base Theorem is going to be easy. All right, I think what I'm going to do, let's see. I'm going to pause here. I'm not going to give you any more for the day. I think you have had plenty. There is only one problem left here, which is this one, garments manufacturing. What do you need to do? You need to follow the exact same procedure for solving this problem, and you will get it. This is kind of like, this is Base Theorem problem, but this is more similar to the traveling salesman problem. So try to kind of follow along the traveling salesman problem, and then you'll get it. But I'm going to stop here for the day. However, I will be doing this problem in the next class. So I want you to try it. I want you to look at the video lectures and then go ahead and make sure that you try the homework problem and come back on Wednesday. And we're going to start off with this problem on Wednesday and then go from there. And the spam filter, ignore it. We are not going to do it. Next, we are going to start talking about fundamental counting principle and permutation and combination and binomial distribution, as well as Poisson distribution. I might talk about Poisson distribution, but not sure. But binomial distribution, for sure, I'll talk about it. All right, folks, thank you. You have a good day, and we'll talk to you day after tomorrow.
Thank you.
Thank you.
Thank
you.
you.
Thank you.